Thank you guys very much for coming to the talk today, the mathematics of modeling. So let's read the description. Purpose of this talk is to show the mathematics that provide the foundation for predictive modeling, demonstrate a unification of various predictive modeling methodologies, and point the way towards the creation of models which are simultaneously precise and explicable. I thought my razor was dull until I read that introduction. So let's get on with it. Okay, so what's going to be the path forward here? Well, first I'll give a brief explanation of who I am. Then we will talk about the mathematics that I claim underlie almost all the predictive modeling that we do. Once we have understood that properly, that will allow us to see models from a particular point of view, which will allow us to think in terms which help to unify the methodologies that we see presented in a somewhat, at least that I have seen, presented in a somewhat disparate fashion in times past. And hopefully this will lead us to the idea of explicable precision. And what do I mean by explicable precision? What I mean by that is having a model which is not only precise with respect to extracting as much signal out of your modeling variables as possible, but that you can also explain to people, right? Because people will oftentimes talk about model opacity. They'll say things like, well, it's a black box. You know, the model's great, but it's a black box. What is it actually telling us? And my claim is that if we look at things from the proper perspective, we'll get a clue about that. Of course, I want to be mindful of time because I don't want to prevent anyone from going to lunch. Okay, so who is this guy? So I hope you'll at least allow me 5 minutes of your time beyond this introduction. I'll buy that with some credentials here. So my background is actually in theoretical mathematics. I have a PhD in functional and complex analysis. And I'm also an associate of the Casualty Actuarial Society. I've also worked in data science for about 9 years, or you can call it R&D, or you can call it predictive analytics, or you can call it predictive modeling, whatever the nomenclature of the day is. And before that, 2 years in operations and IT. And so I've been lucky enough to have been both a practitioner of modeling, of predictive modeling, as well as having the formal training in a lot of mathematics that underlies it. My area of research is in the application of theoretical mathematics to data and actuarial science. And so what are the goals of this talk? There's 3 of them: clarity, unity, and collaboration. And so with respect to clarity, what I mean is that I want to clarify what exactly it is when we're doing data science. Data science is, of course, a hot term. It's been thrown around. In fact, going through some old Facebook posts recently, I found someone posted on my wall, it was an article about data science. They're like, this sounds like what you do. And I wrote back, that's stupid. We're already doing that just by that's just a different name for the same thing. But nonetheless, I lost that. And now data science is the term when you're talking about doing statistics or predictive analytics and that kind of thing. But I want to be very clear about what it is we're doing, because I think once we have a better, clear understanding of what we're doing when we're doing predictive modeling, that will help us to, like I said, unify the different techniques. And finally, collaboration. So here's the deal, is that much of what I have written, both here in the slides and also elsewhere in the articles that I am writing, the reason I'm doing that is because I haven't found it anywhere else. And now this is not to imagine that I'm a pioneer. I presume that the fact that I haven't found it anywhere else is my inability to do really good research beyond the first page of Google results. And so I'm hoping that the outcome of this talk is not only going to be useful to you with respect to your day-to-day work of building models, but it's also going to provide a foundation for actual research in data science, which will help us propel the discipline forward. And I hope to make that case to you throughout this talk here. So let's get into the mathematical foundation of predictive modeling. So this is how I typically see predictive modeling or data science put together. People say things like, data science lies at the intersection of technology, mathematics, and computer science. you got a little bit of statistics in there, you got a little bit of programming in there, you got to figure out how you're going to implement the math, and then, it's like, what's your technology stack going to be? You're going to do this in Windows, you're going to do it in Linux, who the heck knows? And so it's like, it's this hybrid discipline is often how it's presented. And then the next thing you do is you look at the course catalog and you see something that looks like this. And so what is this? And this is the sort of methods that are used when you're doing predictive modeling, right? So you've got your generalized linear models, you specify the method, then all these things come with it. There's the functional form implied by the method. There are the features of the method or the predictors or your X values and that sort of thing. Perhaps transformations of them. That's what I guess in the features column. There is some method, or not method, but there is some notion of an error that comes with each one of these things. And so with respect to GLMs, for instance, the error function that you are trying to minimize is determined by some distributional assumption you make. You say, I think that my quantity of interest conditioned on my predictor variables has this kind of distribution that tells you your error function. And then there's a minimization routine. So again, in the case of GLMs, if you look at the software, it's like you get to select from a bunch of different ones, or you could use a tree, or you could use random forest, or you could use Mars, or you could use neural nets, single layer perceptrons. And there's all sorts of coursework that you can do within each of these things. Each of them has a different functional form. Each of them has features. Each of them has some different error function that goes along with it. Each of them has a different minimization routine. And so when I started actually doing practical work, one of the things that came to my mind was, well, gee whiz, why is it when you talk about trees and you're trying to figure out how to construct a tree, you're looking at things like Gini impurity, or information gain. But when you're doing a GLM, all of a sudden you're concerned with Poisson deviance. It's like, well, gee whiz, pal, like why is it when I change the functional form of my model, does my error change all of a sudden? It's like, why, what's the connection there? And that never made sense to me. And moreover, if you look through the functional forms I have listed here, you start to see that I've actually made some, well, as daring as you can be at an open source conference, rather daring statements about the nature of these things. So for instance, I've written trees in random forests in the same way. I've used the same formula for that. And so it's like, well, how different are trees from random forest at the mathematical level? And then you can also see that the GLM actually encompasses the single layer perceptron as I've written it up here. And so in a certain sense, you can think of single layer perceptrons, neural nets, as being GLMs in a certain sense, if you are willing to abstract to a sufficient level of generality. Okay, so now we get to my favorite part. So after you go through that, you take your bachelor's in data science and you learn about all these different techniques. You learn about Mars, you learn about neural nets, you learn about GLMs, you learn about trees, and then you get to ensemble models. And so if you go and look at what's written up in Wikipedia with respect to these things, it says, oh, I didn't cite it. Oh, shoot. It says, use multiple learning algorithms to obtain better predictive performance than can be obtained from any of the constituent learning algorithms alone. It sounds really nice, but it's really just this. So here's the thing, is that I understand from a business standpoint, if three guys come into the office, and you're saying to them, hey, look, what are our projections for next year? And the first guy says 1 million, the second guy says 2 million, the third guy says 3 million, you go, 2 million. Fine, I get that from a practical standpoint. But from the standpoint of actually advancing data science, it's just like, well, you're just averaging things together. That's sort of, it's pragmatic in a certain sense, but it's sort of the intellectual equivalent of falling on one sword. Okay. So, like I said on the last slide, this brings up a few different questions. One, is it the case that functional forms, error measurements, and minimization routines be packaged together? Is that of some sort of mathematical, ontological necessity? Is there a canonical way to select a functional form and its related features? Is there a canonical way to select a measurement of error? That's a good question. Is there a canonical way to select a minimization routine? So the idea is the chart on the last slide, right? You've got those columns. You specify your methodology, that gives you your functional form, that gives you your error function, that gives you your features, that gives you your minimization routine. It's not clear to me that all these things have to be coupled together. Since it's not clear they have to be coupled together, we can examine them individually. And then as you examine these things individually, the question is, well, is there some sort of canonical way to do some sort of selection here? And so I believe the answer is yes, from a certain standpoint. We will not address the other questions throughout the course of this talk. Very briefly, though, there are at least two canonical ways to select a measurement. One is that the minimization of sum of squared errors always works, and that's because of a property of what's known as the conditional expectation, which we'll talk about in a moment. Then the other thing comes from the maximization of the likelihood function. So if you have reason to believe that the quantity of interest, that its conditional distribution when you specify your predictor variables is something, and so the obvious example of that is if you're looking at a 0-1 variable, right? It's like, well, that distribution. It's Bernoulli, that's all it is. But for more complex random variables, it's not always clear. Is there a canonical way to select a minimization routine? My experience, no, but I'm open to suggestion. In my experience, theorems which demonstrate different methods of optimization often have examples. So it's like, if you read a textbook on numerical analysis, it'll be something like theorem, here's a method, here's a set of conditions where it works, here's the proof that it works, here's an example where it fails. Okay. So now let's try to reimagine data science, but let's do it at a bit more rigorous level. And so here's how I actually imagine data science. I imagine that it looks like this. And so while data science makes use of technology, mathematics, and computer science, I don't see it as a Venn diagram. I see it as a pyramid. And this isn't just because I studied math and I've got a dog in the fight that math is at the bottom of it. It's because there's an order of operations here. And the order of operations is that math indicates what to compute. Computer science determines the implementation, and technology is the tool for the computation. So it's not a Venn diagram, it's quite sequential. And to illustrate this in the easiest way possible, I'd like to bring back to mind your friend and mine, the very first easiest model in any analysis that you're doing, our friend, the sample mean. And so, of course, you learn about the sample mean when you take your first class in statistics, right? But what seems to not always be evident to people is that there are literally an infinite number of calculations you can do, right? There's an infinite number of numbers, there's an infinite number of computations. And so why do you look at that when you could look at that? Instead of taking the sample mean of your data, I say you take its product, you find the cosine of that, you exponentiate the result, and then you add 54 to it. No takers? Okay, so why do we care about the first computation and not the second computation? Why do we care about the sample mean and not that other nonsense that I put up there? And the answer is that the calculation of the sample mean is a well-developed theory underlying it, right? We know, assuming that your x's are identically distributed, and independent. We know from the strong law of large numbers that, as n gets large, that thing converges almost everywhere to the sample mean. We can also make a statement about its distribution, right? The distribution of the sample mean. It's like one of the greatest theorems in all of mathematics. It's almost literally a something for nothing theorem, because it doesn't matter the distribution of your x's as long as your n gets large, you know that the distribution of the sample mean is going to be asymptotically normal. It's like, yes, that's great. That tells us something. What do we know about the second calculation? Absolutely nothing. That's why we do the first and not the second. And so that's the deal, right? Is that the reason why mathematics is at the foundation of data science is that mathematics tells you what to compute. It points you in the right direction. The field of potential is infinite. There's an infinite number of actions you can take. There's an infinite number of ways you can walk out of this room. There's an infinite number of computations you can do. Which ones are useful? That's what the math tells you. And so just as with the sample mean, that there's a well-developed theory underlying it, the question then becomes, well, shucks, is there some mathematical theory that addresses predictive modeling? And my claim is yes. And so to get at that, let's think through for a moment what we're trying to do. And this is roughly what we're trying to do in most of predictive modeling, which is that people often they desire to estimate a quantity of interest using known information, right? It's like, what are sales going to be this month? What's the probability that a person lives longer with this medication as opposed to that medication? These are all quantities of interest, and we want to estimate them. And we often, in data science and in the open source world, in the modeling world, we often use the word predict, right? Because when you're building your models, when you're using Python, when you're using R, even when you're using SAS, I know SAS is not open source, but even when you're using SAS, you still have the syntax of the method is like, PRD, in the output, right in the output. And so we have adopted the language of using the word prediction to specify the estimate of the quantity in which we're interested. Well, another way you might phrase that is, instead of what would you predict using given information, the question you might ask is, what would you expect using given information? I've handed you the predictor variables. What do you think is going to happen? What would you expect? Well, it's always mathematics to the rescue, because what mathematics does is it formalizes our language and our intuition. And so the mathematical formulation of what would you expect given certain information, that's what's known in math as the conditional expectation. It's what you would expect from Y, but not just the expected value of Y. It's what you would expect of Y given certain pieces of information, given your X's. And this itself is a random variable. And now you might say to yourself, gee whiz, Ian, hey, that's great. How does that help? You formalized our intuition, and awfully nice of you to do so. But all you've done is you've just written some letters on a piece of paper. How does it help us to do our modeling better? Good question. And so what we're going to go through now is we're going to go through a reduction. We're going to take that which is abstract and we're going to make it very concrete. And this will be accomplished in about 4 or 5 steps. So what's the first step? Well, the first thing to understand is that the conditional expectation of a random variable is what's known as a sigma measurable random variable. Okay, that's kind of graduate level probability. How does that help? Okay, fine. Well, it just so happens that when you have sigma measurable random variables, what that implies is that you can find a function on Rn into R such that F composed with all of your predictor variables, equals The conditional expectation. And so that's just a run-of-the-mill result, and you can find that in Billingsley. Well, that reminds me, the slides for this contain all of the references. So if you want to look up any of the particular theorems and results, you can. Okay, so we've done a bit of a reduction, right? We were at graduate level probability. Now we're in Calc 3 because we just have a function defined in Rn. And of course, you do deal with those in Calc 3 all the time. You get your nice surfaces. Okay, cool. Well, how does that help? Well, here's the deal. You've got a measurable function on Rn. That's where we are right now. And you say to yourself, measurable. What does that mean? Well, it's an abstract idea from measure theory, but roughly what it means is that you can talk about integrating this thing in very brief terms. It means you can talk about integrating this thing. Its integral might be infinite, but you can at least talk about it. There are some functions that you can't even talk about the integral. So that's still kind of abstract, but we're making progress here. Well, it just so happens that if you have a measurable function on Rn, you can approximate that measurable function with a continuous function which equals the measurable function, except in a little bit, just a little area, just a little area. But everywhere else, they're equal. Everywhere else, the measurable function is equal to this continuous function. And that's not all. Behind curtain number 2, this continuous function has compact support. What does that mean? Okay. Support is where a function is non-zero. And that support is compact. What does that mean? In Rn, that means you can put it in a box. So compactness is an idea from topology, but in Rn, it has a very simple notion behind it. It just means you can put it in a box. And so therefore, what you get is you get something that looks like this. So here, the green is where our continuous function is non-zero. Outside of that set, the continuous function is 0. And this function agrees with f, it equals our measurable function, except on a set of very, very tiny. And you could make that set as arbitrarily small as you like. Okay. So now what we've got is we had this abstract idea, right? This abstract mathematical object, the conditional expectation. We said, hey, it's actually just a function in Rn. It's a measurable function in Rn. Oh, actually, we can approximate it. We can approximate it with a continuous function on Rn to any degree of accuracy that we like. Okay, well, now we're in business because we know what continuous functions are. Measurable functions, kind of hard. But a continuous function, a pre-calc student can tell you what that is, right? It's a continuous function you can draw without picking your pencil off the paper. So now we just got to deal with this weird looking region here. All right, well, here's what I propose we do with it. And you'll just have to go with me for a moment. I say it's going to be more convenient for us to put the support of this function, to put that green area into the unit square. You'll just have to go with me on it. The utility will become evident later. And how are we going to do this? Well, the usual way you do this. So you're probably very familiar with, say, standardizing your predictor variables, right? Where you subtract off the mean, you divide by your standard deviation. That's just what we call an affine transformation, just a shift and a shrink or an expansion. So we'll do the same thing here. So we will shrink the support, and then we'll move the support. And so now the support lies in the unit square. But remember what the support means. The support means is that outside of that green area, the function's 0. Okay, well, fine. Then we can just imagine that we're looking at an arbitrary function on the unit square, and outside of it, it's 0. Okay. So what were the steps? 1, math formalizes your intuition. What you're really doing when you're doing data science, for the most part, is you are trying to estimate the conditional expectation. The conditional expectation is a measurable random variable. That measurable random variable can be approximated to any degree of accuracy with a continuous function. And then you may as well imagine that continuous function is defined on the hypercube. So by hypercube, I just mean the unit interval, the unit square, the unit cube, and then the unit hypercube in n-dimensional space. And so now we're in good shape, because now what we can say is, for all practical purposes, the conditional expectation is a continuous function on the unit hypercube. We have a very concrete idea about what it is we're trying to achieve here, continuous function, and we've got a very concrete idea about where it lives. It lives on the hypercube. And this is what I claim is a very useful lens for predictive modeling, and it's the lens for the unification of various predictive modeling methodologies. Okay, unification of methodology. So here's the deal, is that now we can just pretend that we are trying to estimate a continuous function on the hypercube. Well, who knows how to do that? Well, it just so happens that that is precisely an area of study in mathematics. It has been for years. Probably one of the first theorems relating to that is the Weierstrass approximation theorem that was proven in the 1800s. That was on the unit interval, approximating continuous functions on the unit interval using polynomials. But you can also do it on the hypercube. So multivariate indicator functions can, that is to say things that turn on and off, those things can approximate any continuous function to any degree of accuracy on the hypercube. How does that relate to the earlier slide? Indicator functions, when you look at sums of products of them, a sum of a product of indicator functions is a tree. And so what this is saying is that trees themselves can approximate, they can get all of the signal out of, they can get all of the signal out of the thing that it is you are trying, or your predictor variables, I should say. And now what's interesting about this is that what's interesting about that particular piece of information is that when the guys were developing the tree methodology, so this comes from 1984, this is a Friedman, they write, the author states, binary trees give an interesting and often illuminating way of looking at data in classification or regression problems. They should not be used to the exclusion of other methods. We do not claim they are always better. They do add a flexible, non-parametric tool to the data analyst arsenal. So they weren't even thinking in those terms. The guys who did trees originally, they were just like, here's another technique. Just so happens that it works all the time. Good for them. What else? Multivariate polynomials. Those can approximate any continuous function on the hypercube. That comes from our good friend, the Stone-Weierstrass theorem. So Weierstrass gives his approximation theorem in the 1800s, and then Stone, I believe an American mathematician, goes ahead and generalizes it to a fairly large degree of generality. What else? Neural networks. Neural networks, that's why neural networks work, as it were. And so I don't know if you've had the same experience that I have, but, and there's really no reason to believe that you have. But when I look up things related to neural networks, people will sometimes say things like, we don't really know what's going on in there. We don't know how it works. It's kind of a black box. It's like, no, it's not. Cybenko proved in, I believe it's 1987, that, yeah, that particular functional form, and that's why I stressed single layer perceptrons on that one slide, that particular functional form can approximate to any degree of accuracy continuous functions on the hypercube. Trigonometric polynomials, for our good friends in electrical engineering, let's not leave them out. Those can also, univariate or multivariate, can approximate continuous functions on the hypercube. And in a univariate sense, piecewise linear functions can approximate continuous functions on the hypercube. I think this result holds in a multivariate sense. I have not seen a proof for it. Again, if you read the original paper on Mars, Multi-adaptive regression splines. There we go. Multivariate adaptive regression splines. If you read that original paper, it's just like the guys who wrote about trees. In the paper, they don't say, hey, this works all the time or this works sometimes. They don't even address it. They're just like, here's another technique. It turns out it does work in a univariate sense all the time to approximate continuous functions. I think it works in a multivariate sense. I'm in the midst of trying to prove that. We'll find out. Okay, and then just kind of a useful thing to observe that a lot of these techniques, trees, polynomials, piecewise linear functions, trigonometric polynomials, these are actually linear combinations of a certain set of functions. And why is that useful? Well, because again, that's precisely a particular branch of mathematics that says, okay, here's a set of functions. When I take their linear combinations, can I approximate everything? Yes or no? So that is a sort of an area of research in math. Okay, and so now what I wanted to do is just give you some, how we're doing on time. All right, what I wanted to do is give you some examples of this in a univariate sense. And so here's the idea, is that I tried to create a univariate function which would give the average Calc 1 student a heart attack when you ask them to differentiate it. And so that's this function here. And so that's your conditional mean. And then you just generate some data around it. And then the question is, if you are thinking in terms of how can I approximate continuous functions on the hypercube, and what I just told you is true, that those sets of functions can approximate continuous functions on the hypercube. Just knowing that, the data itself can tell you how to construct your predictor. So here's doing it using step functions, using indicator functions. So this is a one-dimensional tree, if you will, or a tree with depth 1. Here it is using polynomials. Fix it up right away. Piecewise linear functions. Obviously, this one goes off the rails a little bit at the end, but it still has a correlation of 0.97. And again, the data itself, along with thinking about things in terms of, can I approximate a continuous function on the hypercube? It just tells you how to construct your model. Okay, and this leads to the idea of explicable precision. So, like I said, we have to think in terms of functions which are continuous on the hypercube. What's the path to victory? Well, you choose a functional form which is intuitive. What do I mean by intuitive? Well, this is where we get to the question of model opacity, right? So, people often refer to neural networks or random forests, or like, it's a black box technique. It's like, maybe. Model opacity is a subjective judgment, right? A neural net makes sense to me. Simple linear regression does not make sense to my mother. So just a line through data is just too much for her. So model opacity it's a subjective thing. So when you're choosing a functional form which is intuitive, what I mean by that is you need to be thinking in terms of what would the stakeholder of the model accept as evidence. Choose an error which allows one to make statements about convergence. So here's the thing, right, is that we talked about how do you select your error earlier. And the answer is, well, mathematicians have spent some time thinking about what it means for things to be close to one another, right? Like that's what you're doing when you take Calc 1 is you're looking at limits and you're saying you got your delta and epsilon, and every Calc 1 student hates that when they see it for the first time because you have to figure out your delta so that your epsilon works out. And it seems easy for linear functions, but when you do the quadratic example, it just causes all sorts of consternation. So mathematicians have spent a long time thinking about what does it mean for things to be near each other? And there are different ideas about what it means for things to be close to one another. And we've actually already seen two in this seminar so far. So earlier we mentioned the strong law of large numbers, that your sample mean converges to the mean of the distribution. That is what's known as almost everywhere convergence, or almost surely convergence, almost sure convergence. We also mentioned the fact that we know the asymptotic distribution of the sample mean, which is that it's asymptotically normal. That kind of convergence, saying it's asymptotically normal, that kind of convergence is what's known as convergence in distribution. So there's multiple ways that you could talk about things being close to one another. So whatever measurement of error you select, make sure that it coheres with some well-developed theory, we'll say. Choose a selection scheme which achieves the convergence you want. So again, this gets back to, why I'm not saying you shouldn't be looking at Gini impurity, but my question is, how does Gini impurity, when you're looking at it, help you achieve the kind of convergence you want? Choose a selection scheme which tends to parsimony. So parsimony, you can actually speak about that objectively. Model opacity is a subjective judgment. Parsimony is not. Parsimony is how many parameters are you estimating for your model? So let me give you an example. So thinking in these terms, thinking about how do I approximate functions which are continuous on the hypercube. A colleague of mine 4 years ago, we set about to model a particular phenomena, and I was going to use my technique thinking about this, and he was just going to like hit it with stuff, just like out of the box, throw it at the problem, see what happens. Okay, so in terms of model precision, I have to admit, he won. His Gini was 0.77, mine was 0.76. I will concede that. However, I use a generalized linear model, mostly with primary effects, few two-way interactions, just one or two three-way interactions. I had 151 parameters. He had 10,000 parameters in his neural network that beat mine. And so, I feel like if I had an extra 9,849 parameters lying around, maybe I could have gotten a little bit more Gini too. So it's like, yeah, okay, fine. He beat me in terms of precision, but his model was not parsimonious. Parsimony in the context of modeling is essentially epistemic humility, right? Because for every quantity that you are estimating, you are making a statement about what is true. And you want to make as few of those as possible because the world's like really complicated. And finally, prove theorems to make sure you are right. This is what seems to be lacking in a lot of the literature I see in data science, which is that, like I said, Bremen, when you get this right, Bremen, when he was talking about trees, he's just like, here's a tool. And then when the Mars paper came out, it's like, here's another tool. GLMs, McCullough and Nelder, you can go back and look in their book. They have a whole chapter about what happens if your response isn't nonlinear or isn't linear with respect to your predictor variable. But the whole chapter in there, it doesn't tell you at all how to even think through how to figure out what goes in there. Other textbooks I've read that I loaned out and has not been returned to me yet. But I have another textbook that it says, what if your response is nonlinear in your predictor variable? And it says, I don't know, try a square root. How about a log? It's like, no, wrong. No, what you need to do is you need to posit sets of functions which can approximate continuous functions on the hypercube. You need to show that they can. And the more sets of functions you have, here's the key, the more sets of functions you have that do that, that allows you to select from a greater set of possibilities, and that increases the probability that there will be some set of functions which not only are precise, but explicable. There will be some set of functions that your stakeholder will go, yeah, I understand that. That's one of the reasons I like piecewise linear functions, for instance. It's like connect the dots. How hard can that be? Don't ever tell your boss, hey, just connect the dots, pal. Don't do that, or step functions. Again, because step functions in a univariate sense, what is it doing? It's grouping together what's going on there. So yeah, that is, there's a lot more in here, and these slides will be available, but we are about up on time. So I think I will end there. Any questions? The references, and feel free to reach out to me because I love talking about this stuff. And that was the whole point. So I feel like I'm doing this by myself. So hopefully this has been useful to you, and maybe it'll be useful to me. What's up? Oh, sure. All right. Well, thanks you guys for listening to me ramble on. I hope you have a great lunch and hope you enjoy the rest of the conference.